Hello and welcome back to the Geode channel. This is my latest talk that I've just given out in Manila, Philippines for CPEX, the Southeast Asia Petroleum Exploration Group. On the third, well, actually, I present on the 16th of June this year, 2026. And so I've recorded it here so that I can share it on YouTube. This talk is the understanding the complex interplay of sediments in a fluvial-deltaic-shallow marine setting and examples from the Sunda Shelf, Malaysia. And I'm going to utilize sort of modern day examples, or at least back to the latest, the lower glacier maximum, to show you, to illustrate what the environment would be like during the Miocene. So the agenda, we're going to obviously we're going to identify the location and stratigraphy. And as we can see here on the map, we have what we're discussing here. This is Sarawak here. This is the South China Sea, the Spratly Islands here. There's a massive way. We see this sort of darker color is the deeper water. And we see here, this is known as the Sunda Shelf. And this is this shallow platform that surrounds Singapore, Malaysia, Thailand, and goes obviously here into the straits here, the Malacca Straits, and then we obviously have this massive where we have that subduction zone. We're going to look at a typical log and reservoir characteristic of the Miocene incised valleys of the Balingian Province, Sarawak. A typical log and reservoir characteristics of the Miocene tidal marine setting, Penyu Basin, and a typical log and reservoir characteristics of the Miocene deltaic sediments of the Malaysian Thailand Joint Development Association or Adventure. And then we're going to just look at some of the petrophysical issues and the summary of the types of sand bodies that can be identified and used to create a static geological model. So in terms of the stratigraphy of the Sunda Shelf, and all my references will be down here, where you can obviously acquire them for your own reference. This here is the Miocene, what we were just talking about. We're going to be looking at the Balingian first, which is offshore Sarawak, down here in cycle. It's cycle 2, where we have a sort of clastic sedimentation. We're going to look at the Penyu Basin, which is a smaller basin offshore Malaysia, again in that same cycle. And then we're going to go over, obviously they have sort of different names across the basin, where maybe in group I and J in the Malay Basin. And this is the Portugalian and Aquitanian of the Miocene generally. And we're just going to compare the different types of sedimentation between the whole basin during the same time period. And then just to emphasize that the Sunda Shelf is the largest humid tropical epicontinental sea in the world due to sea level rise in the Holocene. But as we will see, during sea level fall, this allowed it to become this sort of marshy, channelized planar form that across the basin, with some lacustrine sediments, some channels, and some shallow marine. So I'm going to emphasize that point. I'm going to just show you, this is the modern day Sunda Shelf at 0 meters below present day sea level. And we can, obviously see that as it is today, this is all a marine system with a shallow self. Remember that cutoff down here, straight down into that basin. At 120 meters below present level of sea level, which would be during a glacier maximum. So when we have the glaciers forming at the poles, obviously we reduce the sea level considerably, and this has great influence on the Sunda Shelf. We can see that we have these massive river systems, the continuation of these massive river systems, all drawn towards the South China Sea, obviously the the lowest point in gradient, and the shelf is approximately 0.001 degree in inclination, so it's very flat, lots of meandering, but you can see there is an overall easterly trend of all the river systems, and the greatest width there is about 600 kilometers here towards the South China Sea, and then from Sarawak about 200 kilometers towards the South China Sea. So that would be the cutoff one where we have this sort of very steep slope, and we go into the sort of turbidites, the deep marine systems here. This is just to sort of re-emphasize what we just saw. There we can see this is our present day Holocene, where everything's flooded. But you can see during the late Pleistocene, so about 18,000 years ago, you can see these paleo valleys extended. So the Paleo Lima, the Paleo Muka, and the Paleo Oya is prograding. In this case, northerly, obviously because of the coastline. Meandering with these big channels forming small deltas at this shallow marine at the margin. This is a short, a shallow shelf, but with low width, so it's not very extensive around here. And obviously, as we flooded in high sea level stand, as is today, we see that all these valleys are drowned, but you can identify these from seismic data. And when we look at the Southeast Sundaland in the Miocene, so we're going to look at an area around the Balingian, where the Bayan field is here, we can see that the seismic, or certainly the vintage seismic, is very difficult to interpret. And that's because there's many coals forming, like very laterally extensive coals, during, obviously, because we have mangrove swamps growing. And this is very hard on the seismic waves, the acoustic waves, to penetrate and resolve between, certainly in terms of the old seismic data. So, and it depends on which field you work on, what data is available. And in this case, it was very difficult to resolve any bodies of sediment beneath or between a big coal horizon. And so it's very hard then to correlate these sand bodies that are also often very isolated as they meander through. This is some typical logs, just gamma ray really, through a section in that area. This is the Miocene cycle 2. These are the high energy sands and gravels. And, we can see that we have multiple clean sands, sort of blocky in this case, and then sort of fining up channels associated with it, and then just spiky coarsening up crevasse splays, which, is typical of this kind of environment. We can see from a close-up of one of those blocky sands that and the core that was acquired. We have a basal coal here, and a sort of washed out sort of paleosol, which as one can assume we're in situ from that. And then we have a influx of coarse material, cross-bedded, gravelly, clean sands migrating, suggesting with this kind of blocky gamma ray that we're in a sort of braided river system. I mean, and this is obviously related to whether we are closer to the shoreline in terms of a braided river system. And we obviously, these sort of these systems migrate laterally continually and also vertically due to small changes in sea level will impact where that shoreline is. Braided systems being more proximal and becoming more meandering distally, but and these correlations were done. These are between those big coal markers, and it was very, very difficult to correlate across to be sure that you were accurate. And I believe they were changing almost daily at one point. When we look at one of the closer up at the cores of one of those braided river systems, and we can see that we get rounded pebbles, prograding pebbles, high energy, very clean, very well sorted, the Tharweg and the braided system. And we also have very clean sands, migrating along some sort of lag here with shale class, rip-up class in between. But a very, very good quality reservoir of cleat sands. When we look at the schematic of the depositional setting of Sarawak, there's a particular example for North Bayan field. We have the Penninian High here, which is the old high. We have this braided river system coming in the upper alluvial plains, which obviously is associated with this braided river system that we just saw in that core with the gravels and this thing. You can look at the size of these things. They're up to 9,500 meters in width. And then as we move down into the upper, lower alluvial, upper coastal plain, we start to get that sinuosity, which is more of those braided river systems. We reduce the width of the channels to, between 100 and 1,900 meters. And then we move into the lower coastal plain where we start to introduce a lot more mud into the system. We'll have clay drapes, we'll have some influence of the estuary, and we get this sort of high sinuosity meandering channels with the introduction of coals and floodplains, obviously. And then a similar sort of width of your channel belt, and then into the delta distributary channels down and into the Sunda Shelf as it impacts. So distributary channels, much smaller, 140 to 650 meters in width. So, and all these can be stacked vertically as you've had minor changes in sea level along along that coastline. And so when we look at, this is the Pleistocene and the Balingian Province, showing north trending paleo-incised valleys offshore Sarawak. And when we look at Sunda Shelf here is 120 meters, this is where the location where we're actually looking at. We see that these are those meandering channels, maybe upper coastal plain, not too meandering, on lower coastal plain, coming off. And these are mapped from geophysical data, so of the seafloor. Here we have the Bayan where we were looking before in that area. When we look at a cross section between this across the Balingian, these are the boreholes BH1, BH1 across this area to BH7. So this is like 1.8 kilometers, 4.5. We see there is a distinctive channel here, a largely eroded channel, which is here. This is the active fill that came in from one of those systems. But we have lots of little isolated channels that continue. And if we go back to that original cross-section that was interpreted from the Miocene, it makes that look maybe a little difficult to have correlated any of these sands, really. They could have been just isolated channels. And maybe, that was just inaccurate and optimistic to correlate between the two, as we see from this section in the Pleistocene that most of these channels are isolated. When we move on to the West Sundaland into the Penyu Basin here, this is the Peninsula Malaysia, and we're now here at this location on the map. We can see from the seismic, we sort of see, bear in mind this is from the Miocene, this seismic, that we are just pulling out an isolated channel. It's still very difficult to discern the smaller channels from the seismic data because some of them obviously are mud filled, they're not always sand filled, and they're very difficult to determine. So you do have to utilize sort of modern day analogs to try and interpret your subsurface. And in terms of a modern day analog, the Rajang River Delta, Sarawak, is a perfect example of what we're looking at in that Penyu Basin. We can see that we have lots of meandering channels, lots of creeks, lots of mangroves, lots of mud, and lots of sand that are migrated into the basin and form this sort of the old Sunda Shelf during the Miocene. Would probably look a lot like that around the Penyu Basin. When we look at the processes that to interpret these estuarine delta Fluvial-deltaic-shallow marine systems, we can utilize this graph. And here we see this is the river system, this is the delta, and this is the shelf. And obviously all of these diagrams are connected in terms of where they're orientated. So obviously here is the river and here is the river. So if we look here, this is at the energy levels. The red is the total energy levels. This blue dashed line is the tidal current dominance. So this is energy levels here. And this is, the three different curves. So the red is the total, the dash and dot line is the river currents. The blue dash is the tidal marine. And then this black is the wave energy. And what we can see, of course, is as we flow from this alluvial plain through the tidal fluvial channel, we have a domination of the river current. But we do still have a strong tidal current. Okay, at this point, they can go kilometers and kilometers, 200 kilometers upstream, if not more. So we have a unidirectional flow, though, even though there is tidal currents, a dominant unidirectional flow, shall we say. And in terms of the grain size, we have, because we have such a powerful fluvial system, we're putting in predominantly sandy grains. And this is this blue line here. This is the blue line is the bulk grain size. The sand grains is the dash line, and the suspended sediment is the orange line. And so what you can see here, we have a low amount of clay in the system. We have sand grains, and we have a dominantly unidirectional flow until we have a sort of increased amount of tidal current. As we move towards down channel, you can see here we have this tidal current maximum, and that's because of the funneling of the flow. So as the seawater comes in, as tide comes in, it enters the funnel and increases in velocity. So the actual tidal maximum in velocity is somewhere mid peak here into the distributary channel. And we start to see the river domination of that flow is reduced, and the tidal maximum is starting obviously to reduce after that. And there is a mixed energy system. And what we see here in this area is this suspended sediment concentration being high, the bulk, the sand grains being low, and obviously the lowest point of the bulk grain size. So we increasingly bidirectional, but ebb current dominance, towards the sea. And then we have, as we move to the this bidirectional flow, we have the waves energy coming into the system, where we can increase the amount of sand grains, and the total energy obviously increases. The amount of the bulk grain size increases, and we can create obviously clean sands around here, but often bioturbated. So just understanding this sort of distribution of where will your sand be, one in your fluvial, and one in your sand wave bars, distributed amount tidal bars. And here, although a lot of sand, we've got a lot of mud. So we can sort of place ourselves by understanding the proportions of sand to mud. So here is a typical log through that Penyu Basin. Here we have the calipers. We have the markers. This is the chord section up here. We're using a gamma ray shading here to try and to determine our sand bodies. We've got the resistivity here. We've got the neutron density curves with just small amounts of crossover. Here we're using the NMR. We've got the permeability Timor equation and echo equation utilizing the NMR just to show both. We have the bound fluids from the NMR, the nuclear magnetic resonance. So this is the amount of pore size that's available. This is bound, and this is the total of pore fluids that would flow. So BF and total porosity in blue. And then we have the just the shading of the permeability from the NMR and the porosity from the NMR, which gives you obviously an increased area of shading of potential flow. This is from the image log, but colored in a binary. So a yellow for sand, green for shale, gray for absent data. So that we can easily highlight where we see resistive sand. And then this blue is the calcite proportion that is derived from the elemental capture spectroscopy curve, which is here, which is a curve that is like a spectrolith, and it acquires, how much calcium, potassium, sulfur, etc., is in the system. And this is just the proportion of calcite to try and indicate whether we have increased cementing of our sands. And then what we can see here is a truer indication of where our sand bodies are and how much sand. And what you can clearly see from this log is that we have a lot of sand in the system, even when our gamma ray shades shale. So when we look at our facies that from both core and image logs, we can see clearly. So this is a static image. We see where it's resistive here, conductive here. This is just the scale, and we can see clearly from the dips. So here is 10 degrees, 20 all the way to 90. Our dips are going south here and south west or westerly, and we about 10 to 15 degrees, and this is from the cross bedding. What we see here, the other sand, these are just sand facies here. We've got laminated sand, sort of clean, thin sands, and some intralaminated sand. We've got rippled sand bodies here with, we can very difficult to discern the exact sinusoids. Biotubation sand with lots of biotubate nodules, and then actually we were able to see rootlets in the sand where we are at the top of a sequence. When we look at the core here, we can see that we have these sort of reactivation surfaces from the cross bedding. We can see mud cracks. We can see syneresis cracks here around here. From changes from fresh water to marine water. We can see biotubation, we can see lamination around here. So that, we see sand, but we can see that there's a lot of mica in the system draping our sand bodies, which would obviously increase the gamma ray. And we have biotubation, which would increase the mud into our gamma ray. So when we have a little look at one of those high gamma ray sections that we may have discounted in terms of open hole log analysis, here is this chord section, which we're looking at here. When we look at the NMR, we clearly see that we have increasing pore throat size, pore size as we go up. We see the T2 cutoff, we see large pores. We can see that we go from a sort of shaly down here into a sand from the image log. Yes, we have this sort of calcite increase, but that could be just we don't know if that's blocking pores. And when we look at the core, we can see it's clearly heavily biotubated and bringing in clay into the system, but still very, very sandy. So we can see that in the Penyu Basin and many basins that have a sort of very strong mix between sand and mud in that upper estuarine area, we cannot identify the good sand at all from open hole logs. And we're using the NMR would be your primary source to determine porosity. When we look at the estuarine distributary channel, we've got a sort of average body thickness body size 25 meters in this case. We see these sort of fining up bodies. Here we are. We interpret it to be a little bit up here. We're still strongly fluvial. We've got a sort of fining up sequence. We've got a high cross bedding. We've got large pores here at the bottom associated with the cross bedding. We've got the very clean sand because we've got the high energy fluvial system. We have rootlets at the top, paleosols, abandonment of the channel as it's migrated. And in this case, we've got abundant of calcite, and cemented layers. When we look at a sand body that's a shoal, tidal channel, or tidal flat, so just around the mid area of the system, if you remember, we are increasing our sediment suspended load. We see that, we're coarsening up now. We've got multiple stacked coarsening up features. We have cross-bedded, not always hummocky. I've written hummocky, but it's not necessarily true because we're going to expect our hummocky to be out here. But certainly if there is some wave influence down here, we would expect, but certainly cross-bedded. we'll have a dominance of the heterolithic facies, so the interbedded sands and shales, and we have sort of fine to medium grain sands. And again, we do see the sort of cyclicity of the calcite cement. But the sand bodies are smaller now. They're about 3 meters thick, stacking on top of each other. And when we look now at the mouth bar down here, where we obviously have introduced the wave energy, we do see these larger 15 meters coursing up body based on the NMR. We do see some cross bedding or low angle ripples at the top, but obviously you could, as I mentioned, have some wave activity there. We've got, it is clean sand towards the top, and we have rootlets of maybe abandonment of these wave bars, these mouth bars. But in this case, little to no calcite in this area. And when we think about, this is the Nanchuna, which is out here, so the Penyu is out here. So if we move, these systems are meandering around. When we do get that channel system, when we think of our more fluvial setting, it is meandering and it's controlled in this case by possibly a fracture system, keeping it, in line over those time. But we see that overall northeasterly flow, as we would imagine, towards the South China Sea, but influxes of flow, obviously in those more tidal setting, towards the shoreline of Malaysia, towards the southwest. So, the reconstruction of the paleo systems, it could be a direct analog, of course, for that Miocene during the time, if you were to try and determine paleo currents. And when we move now to the Northeast Sundaland in the Malaysian Thai border up here, now bearing in mind that a ton of sediment is pouring off Thailand at this stage, there's a dominant delta that is flowing into the Sunda Shelf. And of course, we have the rifting that's gone on in the system. We've got the rift climax sediments, early post rift, late post, etc. Part of this basin. We start to look at a little more, a very complicated deltaic-shallow marine system with thin beds. And not saying that the thin beds wouldn't be found in the Penyu, but it's characteristic of this upper area. And so these are low resistivity, low contrast pay is obviously a difficult because the neutron density logs tend to converge without crossover, and the resistivity ranges between 1 and 3 ohms, and the gamma ray is high. So a bit like what we saw in the Penyu, in the bioturbated sands. These are very thin, clean sands with mud. Very, very small. So when we look at this section, this is a typical reservoir, i.e. a clean sand. But this area here is this, LRLCs. You can see that it's very difficult to determine. It's clays and silts with fine sands. But you can see that, we still have good permeability here in this area where we have the clean sands. So the conventional here is in purple, and the LRLC is in light blue, and you can see that your grain size is silt to very fine silt. You have moderate to high UV shale. The lithofacies are bioturbated sands, bioturbated silts. We've got moderate to high gamma ray. Your neutron density are converging. Your porosity is 10 to 20%, but your permeability is as high as 50 millidarcies, and you're less than 3 ohms. So, this is a play that needs to acquire good data and good tools and the image log being one of them, to find these small, thin beds. When we start to look at the sort of core in thin sections showing the reservoir complexity, the brown coloration is the mud. What we see down here is this sort of laminated very, very clean sand in the mud, which is obviously where you're going to get the highest permeability and porosity in those very thin beds. The biodebated fascies, okay, still, having large clean sand areas, but obviously have a very high tortuosity in terms of the permeability path. And then obviously our clean sands, just discrete mud, which obviously would still impact your gamma ray, right? And this is just to show you in the terms of the depositional environment of what we would be seeing. We've seen this this is the Mahakan Delta, Kalimantan, Borneo, and we would be starting to be really just somewhere up here in this area of complex interplay of sand and mud in the system. In terms of the heterogeneity and the impact on the petrophysics, what we're looking at in the Sunda Shelf, or obviously we can all identify the very clean sands in all these plays, but where is the cutoff? Where do you put the cutoff? So in all of them, we're looking for thin beds, heterolithics. There is a shaly sand, sandy shale spectrum, so there is really no cutoff. It's not a case of shading a gamma ray and putting millions of colour and still hoping for the best. You could see from that previous slide of discrete nodules of clay, laminated clay, clay drapes, that we have a real spectrum of sandy shale, shaly sand. We've got extensive and intense biotubation. This is an area of brackish water, lots of sunshine, lots of nutrients, so lots of biotubation. And of course, that's bringing in discrete mud into a clean sand. And then we have sand bodies that are subseismic resolution. So we have big coal indicators masking good seismic quality. Difficult to resolve some of those smaller bodies and what's the geometry. The need of a modern day analog is important to try and size the geometry of your sands. And then little lateral continuation. We can see that from the Pliocene, that these sands are isolated laterally. Obviously, if you follow down the paleocurrents, of course they are, continual in paleocurrent direction. But obviously, if you're, looking across to a sand body, they're not going to be continuous. So you have to be very careful of finding out your paleocurrent direction of where. And as we could see, that most were heading towards the east to the South China Sea ultimately, but many of those creeks are coming at angles, right? Extensive meandering, as we could see, there is, an overall trend, but there is a big meandering. But they were constrained by a sort of tectonic fault regime. So you could see from the Pleistocene that they had remained within their valleys. So although extensive meandering within, they were ultimately constrained. And then mineralization to watch out for: pyrite, chlorite, glauconite mineralization. So glauconite in sufficient quantities has a massive impact on the density, neutron, PEF, and resistivity log responses. It's a complex mineral. It has iron, potassium, and magnesium hydrated aluminium within hydrated aluminium silicates. It's a clay that absorbs a lot of water, which retains a lot of water, and so will obviously influence the resistivity and impact your rock. It's also, iron rich. So any amount of glauconite is going to be misleading in terms of a future prey. And obviously pyrite is very iron rich, so we're also going to impact our log data. And then obviously we have coals and hard grounds, carbonate and siderite that would, be barriers, could be permeability barriers vertically for your reservoir. So in terms of taking what would you take up to a static model? Well, I managed to sort of divide them into three major sand bodies, with our rock type 1 being the very clean sand. We're up in that fluvial distributary channel, fluvial and braided river system, up in the high porosities, high permeabilities, cross-bedded, generally in the direction of South China Sea or northerly, depending on obviously where you're coming into the basin. They're the upper coastal plain. And then we have the mouth bar and tidal flats. Remember, they were the front end of the system with wave influence. This was, in this case, rock type 2, 3, and 4, which was sort of biturbated sandstones, ripple sandstones, laminated sands. Clean to a point. Obviously, they had lots of more clay in the system, so we've got reduced permeability, and less of the cross bedding, but certainly a very good play. And then the marginal play is the shoal, tidal channels, and tidal flats, unidentifiable from traditional logs, which would can make up 60% of the log of the reservoir. So you can imagine there's probably 60% bypass pay. It could have been could have been lost in many of the reservoirs without a proper acquisition program. And so that this is now the some cross bedding, some lamination, but also rippled clay drake ripples. We have much reduced not porosity, same amount of porosity, 23%, but a much reduced permeability due to the tortuosity, but does not mean that it does not flow. So those three types of facies associations are a good method to build a good starting point to build a static model of the Sunda Shelf. And then the rock types, driven from NMR, particularly, and core and image logs to get your good rock types that are bypass, which are very difficult to see, and then take into account, the glauconite in the system that absorbs a lot of water.